Welcome everyone here in our lecture hall in the Färber building. And in particular, I'd like to welcome our guest of honor, Professor Michael Färber. That's why we are all here, and I'm very happy about the turnout. You have a great fan club, so I hope it will grow after this lecture, which you, by the way, will be able to download later in our YouTube channel. So, what are we going to talk about today? And what is Michael Färber up to in his research? The systematic use of artificial intelligence for epistemic purposes represents one of the most pressing challenges of our times, in particular here at a university. Science is producing data and research papers at a pace with which humans, not even scientists, can keep up. And it is not only the quantity of data, but also the challenge to combine very different types, i.e. quality of data in one analysis. Breakthroughs at the frontiers of science more and more depend on mastering these data in terms of quantity and quality. And this is exactly where Michael Färber's research comes into play. He is a true pioneer of AI-driven scientific discovery. He advances the frontier of machine epistemology by developing systems that can autonomously generate and test hypotheses, trace the provenance of knowledge claims, and synthesize evidence from heterogeneous sources. By developing innovative tools like the JD fact decomposition framework and the Ragenta multi-agent QA system, Michael Färber directly tackles the challenge of making complex knowledge both accessible and verifiable, thus enabling new forms of machine-supported understanding and discovery. His integration of knowledge graphs with natural language processing goes beyond technical achievement. It creates novel pathways for extracting nuanced, evidence-based insights from vast and heterogeneous data sources. Through open, richly annotated, scholarly data sets and collaborative platforms such as the Open Chemistry Knowledge Base, he empowers interdisciplinary teams to build and interrogate knowledge in ways previously impossible. This profound commitment to advancing the epistemic capabilities of AI systems, coupled with an ethos of open science and cross-institutional partnership, makes Professor Färber uniquely aligned with who we are, with our vision as a collaborative university where knowledge creation is a shared undertaking and it is fostered through partnerships across disciplines and institutions. Now my things are. So we are very, very proud that in April 2024, at the remarkable age of 36, and we are not age discriminatory here, Michael Färber has joined TUD as a full professor at the National AI Competence Center, SCATS AI, at TUD, and our Faculty of Computer Science, of course. And his active engagement with national and international networks and his openness to interdisciplinary teamwork make him a uniquely valuable asset of SCATS AI and a perfect fit for TUD's vibrant research-driven ecosystem of digital sciences and beyond. And that is exactly why we are happy and we welcome Michael Färber and his family. I learned his parents are with us today in this lecture hall. We welcome the Färber family to the TUD community. Applause, please. So I could go on and on and on, but I will not do this because I have two valued colleagues who come after me, and for good reasons, because they will tell you all the details of the outstanding career of Michael Färber on the one hand, and on the other hand, the strategic role that his professorship has within SCATS AI and also the Faculty of Computer Science, which is, of course, Christel Bayer, our very valued Dean of Computer Science. Where are you sitting? On the left. And not yet, just a second. You will get your turn. And Wolfgang Nagel, the director of our Center for Interdisciplinary Digital Science, KIDS. Here you can see it. And, of course, the lead PI of SCATS AI, which we join with the University of Leipzig. And we will listen to this University-wide Inaugural Lecture, which will tell us more about whether AI can replace scientists. And of course, this is very existential because lots of people sitting here either are already or aspire to become the next generation of scientists. Thank you very much for the people in the background who made this possible. This is my Chief of Protocol, Christine Milkau. It is valued colleagues from our unit of communication and, of course, from the Faculty of Computer Science and from KIDS. I just got to know the coordinator sitting here. So thank you very much for all of you. And now I'm handing over, and I take it that Christel takes the stand first and then hands over to Wolfgang. And don't forget, after the talk, Q&A and a reception outside here, so don't run away. It's great to have you here. Thanks.
Yeah, a warm welcome also from the Faculty of Computer Science. And thank you very much, Michael, that we are very glad that you accepted the offer for the call for the chair called Scalable Software Architectures for Data Analytics. So as our rector, Ursula Staudinger, said, Michael came here to TU Dresden in April last year, April 24. And he is already very engaged at our faculty, so he's a member of the faculty council, but also in the selection committee for the Master of Computer Science. He was even the vice chair, so he's very engaged, and also in other committees. So thank you for all that. Now, Michael did his PhD thesis in 2017 at KIT, what is the precise word? Karlsruhe Institute for Technology. And afterwards, he went as a postdoc first to Japan, Kyoto University, then to Freiburg University, and then back to Karlsruhe, first as a postdoc, but then for, I think, 5 years, or 4 or 5 years, as a deputy full professorship. I forgot the name, sorry for the name of this professorship. but I'm sure it was also in the direction of AI and natural language processing and so on. Well, Michael Färber has a long list of publications, I think more than 200, and he is the winner of multiple awards, including some recent Best Paper awards and many other things. So he is an expert, as Ursula Staudinger said. Well, I would say at the combination or at the intersection of AI, LLM-based AI, and natural language processing. But I think in this talk you go more into the details of the LLM-based AI approaches. But let's see. So, yeah, with these words, I hand over to Wolfgang Nagel from the SCATS AI.
Dear guests of honor, dear Professor Michael Färber, dear Michael, dear colleagues, members of our TUD community, dear guests, welcome to today's inaugural lecture here in the Fritz Förster Bau, and also welcome everyone who is joining us online today. Later on in the channel, the systematic use of artificial intelligence of scientific knowledge management represents one of the most pressing challenges of our time, since science is producing knowledge at a pace no human can follow, creating what we might call a publication tsunami, where valuable insights risks being lost in the sheer volume of information. And you will help. In that regards, Professor Färber's research is particularly fitting and exciting. He is a true pioneer in AI-driven scientific discovery, and his work spans the most innovative frontiers of artificial intelligence. And we need that in SCATS-AI. Therefore, he was the first colleague joining when we hired new professorships. His research combines large language models, knowledge graphs, and graph neural networks with strong connections to neuro, symbolic, and explainable AI. Among the central themes of his work is scholarly data mining, developing AI systems that can analyze millions of research papers to make scientific knowledge more accessible, transparent, and trustworthy. Michael's work is truly at the cutting edge of artificial intelligence technology, focusing on the development of systems that can extract evidence-based insights and turn scattered knowledge into coherent understanding. I think this is an important point. We are talking about AI all the time, but the question is, how do we get benefits out of it, knowledge? These innovations are not just theoretical achievements, they have practical applications that promise to revolutionize how we interact with scientific knowledge as we know it. By combined structured knowledge graphs with the reasoning power of large language models, his research enables new form. Sorry. Ralf. By combining structured knowledge graphs with the reasoning power of large language models, his research enables new forms of scientific discovery that were previously impossible. Since April 2024 already, Michael Färber has served as full professor at the AI Center SCATS-AI, and TU Dresden, where he leads the research group Scalable Software Architectures for Data Analytics, and serves as a unit leader for cognitive AI. Appointed at the remarkable age of 36, he previously served as a deputy full professor for web science at the Karlsruhe Institute of Technology. His impressive task records includes more than 120 peer-reviewed publications, and it's not clear Google Scholar doesn't list it completely. But he has published at leading international venues such as ACL, EMNLP, ISWC, and so on. NAACL, I think, was the last one. And this work has been recognized with multiple Best Paper Awards and prestigious fellowships, including the JSPS Fellowship in Japan, which is really an achievement from the Japan Society for the Promotion of Science. Looking ahead, Professor Färber's research holds tremendous potential for transforming scientific discovery through advanced neuro-symbolic AI approaches, real-time analysis of scientific literature, and trustworthy explainable AI systems that make insights scientifically more accessible and transparent. This is, I think, the challenge we have. This reflects his broader vision of AI not merely as a tool for automation, but as an enabler of new forms of scientific discovery. His successful acquisitions of more than €2.5 million in third-party funding from national agencies, foundations, and industry demonstrates a significant impact and recognition of his work. Beyond his research excellence, Professor Färber is an award-winning teacher who has successfully delivered lectures to an audience of over 600 students. So we are a small group here. And maintains international collaborations with institutions such as Kyoto University, you mentioned that, Crystal, and of the University of Innsbruck. His active engagement in AI policy making as a member of the ACM Europe Technology Policy Committee positions him at the forefront of shaping responsible AI development, contributing significantly to trustworthy, evidence-grounded AI for science and strengthening the visibility of SCATS AI and KIDS and TU Dresden in research, teaching, and AI policy. The central question of today's lecture, will AI replace scientists, is, according to the day, it is provocative. We will see what is coming out. From papers to insight with LLMs and knowledge graphs speaks to challenges that affects every researcher and every scientific discipline, not only computer science. This lecture will explore how the combination of knowledge graphs and large language model is changing the way we work with scientific literature and what this means for the future role of AI and of scientists themselves. It's not just putting a couple of words in Google and then finding the papers and just reading them. It's knowledge insight which drives the detection process of getting the right paper. We look forward to the fascinating insights that Professor Färber will share with us today. His research not only advances the boundaries of artificial intelligence, but also promises to reshape how we discover, organize, and build upon scientific knowledge in the years to come. Thank you, Michael. And we are looking forward to your lecture, and we are very happy that you are in our team.
So, yeah, hi everyone. Great you're all here, that I have your full lecture hall. Strictly speaking, this is my second inauguration lecture. Some of you might know already. Last year at Faculty of Computer Science I've given one. Apparently this was a great success. I'm here now for University-wide Lecture. And yeah, to start with, first of all, you have already heard today the chair is called for Scalable Software Architectures for Data Analytics. So what is this about? I asked myself actually last year when I started here. And the first thing you do is nowadays you ask AI. And this day, I did not ask ChatGPT, but I asked some software called Midjourney, which creates images. So let's see what comes out based on this chair of Scalable Software Architectures for Data Analytics. Voila. So you can see, yeah, here, okay, still some typos, some room for improvement. Maybe, so this was last year, maybe it's much better now. Overall, quite futuristic, but I would say here the chair is actually quite cozy, so maybe a good reason to stay here for longer. All right. I titled my lecture today, Will AI Replace Scientists? And this is, of course, not a random title. I think it's the time to ask this question right now, and not in 5 years, not in 10 years. This is a very important question which we need to address. And happy that you're here to discuss this with me also later on. Maybe a short hand sign who wants to participate. Who will say that AI will replace scientists overall completely? Is there anyone in the room? Thank you for joining. Okay. Who says no, not at all? Mm-hmm. Most of them, okay. Thank you. And some of you are maybe unsure. That's also good. Yeah, to give you a preview, we can say, we might say yes or no, but the point is that at least the way science will be done in some years will be quite different. And this is something to do with this figure here. What can we see here? We can see here the number of publications since 1900. And very obviously, we have here an exponential increase in the number of publications. As I said, this is over all scientific disciplines. I distinguished here between journal articles, in proceedings, and preprints. And we can see, first of all, the majority is based on journals. So this is still quite common. We can also see around the year 2000, it became more and more common to have these in proceedings. So this is basically papers published at conferences, very common nowadays in computer science, AI, and other fields. The idea is here that we have a quicker turnaround. Basically, if you have a peer review, you get the reviews after some weeks or months, and you don't need to wait 1 or 2 hours. And what you can also see is that since some years here, especially so 2020 around, we have quite many preprints. So it shows that this is the next step, basically. Now it is especially common in AI topics. You don't wait until it gets accepted, but you directly upload it on arXiv or some other preprint server as soon as you have finished the paper as good as you think, basically. Yeah, the big question is, of course, what do we do now? We need to mitigate this information overload, or to say differently, how can we transform this information overload into actionable insights? And I want to argue that this can be done to some degree by using some kind of structure. What do I mean by this? First of all, if you think of the scientific publications, this is a lot of unstructured text, you can say. You might have references to other papers that basically you don't really have clues about how this paper is connected to all other papers, to this whole scientific landscape. If you think, for example, of, let's say, anomaly detection in computer science and climate science, there could be overlaps, but it's not really obvious just based on the papers. And here, structure could help, basically. Another point is the terminology. In science, we write in quite specific jargon, as we think this is needed, and often it's needed. But it's also quite complicated. We use different words for the same thing. If you think, for example, in medicine, we have heart attack, myocardial infarction, MI can all mean the same. We can also use the same word in different meanings. Let's say fragmentation, segmentation can mean in medicine something totally different than in computer science, computer vision, for example. So here's another challenge also where structure will help, as I will show you later. Then evidence and traceability. We are used in science to have citations and so on. And also here, citations or in general structure can help. And finally, if you think of this figure I just showed you of this information overload, then it's also important to build such systems that we can help them, the researchers basically, help them to find the right paper, the right data set, and so on and so forth. And nowadays talking of these millions of publications, alone 2 million publications on arXiv, which need to be processed basically. On the other hand, we have this potentially millions of authors and users worldwide which might want to use such systems. So the main point is here, it's not so much that we don't have this knowledge available. We have these publications and so on, but it's more that we need to think about how to synthesize this information, how to make use out of it, and how to bring science really forward. And I want to argue now in this talk, technically speaking, this can be done by knowledge graphs to some degree. So some introduction first, what are knowledge graphs? Knowledge graphs are first of all an explicit semantic knowledge representation, which means we model knowledge, hopefully intuitively, as a so-called graph with nodes and edges. This is what you can see here. So we have, for example, Bob, Mona Lisa, Leonardo da Vinci. These are entities, so real-world things, which are in persons and so on, which appear in the real world. We have relations between them. Bob is interested in Mona Lisa, was created by, and so on. We might have types like person, attributes, and so on and so forth. If you think of knowledge as exists in Wikipedia now, then such a graph, such a structure can be quite large, you can imagine. You might have millions or even billions of nodes and edges. And interestingly, such knowledge graphs even exist already. So we have Wikipedia, we have Wikidata. These are cross-domain knowledge graphs, so modeling very generic knowledge. On the other hand, we also have some domain-specific ones. Here's an example, for example, in the biomedical domain, modeling diseases, symptoms, genes. Also, in the industry, we have knowledge graphs out there. You often just use it, but you don't know. An example is here Amazon with the Amazon product graph, so modeling all products in such a way. And also, Google has used the Google Knowledge Graph or is still using it. I don't know who's still Googling nowadays, but nevertheless, if you think of Google and you just enter a keyword like Albert Einstein, if you think of a person here, for example, then on the right-hand side, you might often have seen this info box, this kind of table. And if you go there inside, we can really see, actually, these are the key facts, apparently, about this person, in this case, Albert Einstein. This is more or less a table or some facts here, but in the background, I can show you here, you have Albert Einstein, and we have these facts like date of birth, date of death, and so on and so forth. All right. So this is the example, the Google Knowledge Graph. I already talked also about Wikidata, another knowledge graphs out there. This is the page about myself. And yeah, interestingly, quite a lot of information about me. So yeah, this is knowledge which we can use. And I myself, I have created such knowledge graphs on a large scale. And I focus particularly on so-called scholarly knowledge graphs. So I want to model the academic landscape, you can say. I have created these knowledge graphs highlighted here in blue, namely SAMOpenAlex, LPWC standing for Linked Papers with Code, MAKG for Microsoft Academic Knowledge Graph, and DSKG for the Dataset Knowledge Graph. Let me go into the first one into a little bit more detail. So SAMOpenAlex is available under samopenalex.org. So this is a knowledge graph which is really massive, really large in size. It's actually one of the largest knowledge graphs out there. And it contains 26 billion facts. So 26 of these nodes, links, and so on. And here's already mentioned what it contains. So basically, we are talking about the metadata of scientific publications, for example, scientific works, authors, institutions, venues, and so on and so forth. Here's an example. So this is apparently me modeled with some key facts, actually more and more also included. I didn't show everything. And then we have also information about, for example, my affiliation. And then we have here papers which I authored, co-authored by others, for example. With information about them, we have information about in which scientific disciplines they are, and so on and so forth. So this is great. This is really because it's great because it's covering all scientific disciplines, and it's also up to date. What's maybe is missing is what I call the scientific key content. So when we think of this information overload, we might need to recommend rather data sets, tasks, evaluation results, and so on and so forth. And apparently, SAMOpenAlex is not capable of addressing these things. But there are a few knowledge graphs out there. For example, I have also created linked papers with code. This is another knowledge graph, which directly goes in this direction. So what does it cover? Well, we can see it here. Papers, repositories, datasets, tasks, methods, evaluation results, and so on. Also here an example. We have, for example, our paper information. We also have the link to SAMOpenAlex, so that's great because then we can reuse all this information. Then we have data sets which were used, tasks which were really addressed in this paper, maybe models which were used, and so on. That's great. However, on the other hand, this is mainly about the machine learning field. So this is based on this website. You might know Papers with Code, which is not really available anymore. And on the other hand, really, people edited this information online. They went through the web browser and then inserted all this information. So it does not maybe scale to the whole scientific disciplines and so on. So there we maybe need to think about information extraction, which means extracting such information from papers. But this is not the focus of this talk today. For now, let's just assume we have this perfect knowledge graph. We have all this information structured in a knowledge graph. Then this is something like being here in a library. We have all the information out there, basically in this case as books. But on the other hand, we also need someone who can use this information. We need a librarian, basically. And the same with knowledge graphs. In knowledge graphs, we have here basically our nodes and edges. But we also need someone, or maybe something, to interpret all this information. And this is where knowledge graphs itself fall short. It's mainly about representing knowledge. But this is where these large language models, in short, LLMs, as you might know from ChatGPT, might come in. In a bit more detail, what I mean by these limitations. So where do this perfectly structured knowledge, these knowledge graphs, fall short? And where do LLMs help? One example is what I titled the language gap. So as a normal person, I, of course, express my so-called information need as a natural question. For example, who are the professors at TU Dresden working on AI and their most cited papers? And on the other hand, these knowledge graphs I showed you so far, unfortunately, don't really understand this question. They understand something like this. This is a query language called Sparkle. In reality, it's actually a bit more complicated, maybe. But it shows that, yeah, we need to bridge this gap between this question here and this query. So how do we do this? And this is where knowledge graphs, yeah, are not capable of, but where large language models can play the role because they can basically understand these both languages. Another point is the complexity and uncertainty. So if we think of a knowledge graph, the knowledge graphs are excellent in modeling these facts, which you might have seen in Wikipedia and so on. Here the example, Mount Everest height 8,848 or 49 meters. And on the other hand, if you use, for example, ChatGPT, you might know, yeah, this is not how large language models operate or generate text. They might say here Mount Everest is the tallest mountain on Earth. There's also valuable information in the sense of that you get a concept of what is the tallest, sets it into context to the Earth and so on. Another example is, for example, you have cat is an animal. This also may be modeled in a knowledge graph, but on the other hand, cats like to sit in boxes could also be useful in reality. And this is not really represented in text typically. So here also large language models can help. Okay. So apparently LLMs are the key. LLMs are trained on this massive text corpora. Nowadays the whole web, you can say, also millions of publications. I guess many of you have used large language models such as ChatGPT for summarizing papers, explaining specific items, concepts, and so on. They are also great in question answering nowadays. Maybe let's give a short example here. In the biomedical domain, you might be interested in a relatively easy question. How does CRISPR differ from the traditional gene editing techniques? So, yeah, if I remember, even during my PhD time, this was solved like this. We had a traditional search. We had a few thousands or maybe millions of papers. And then we had a kind of keyword matching, which means that we have here CRISPR, matching here with CRISPR, gene editing, matching with gene editing, and so on and so forth. And then we had here a ranking of these publications, and then the user needed to read this and so on. Nowadays, it's of course, since some years, completely different. Nowadays, we have LLMs, and they can directly provide here the answer. CRISPR is faster, more precise than older methods, targets DNA, and so on and so forth. So it shows here we transform from retrieving papers to directly delivering the insights. So that's great. Are we done? Well, obviously not. And yeah, here it's already written. Many of you who have worked or at least used large language models might think of, but what about hallucinations? What about inconsistencies? Especially in science, we have a field with where we need a high level of trust. And how can we guarantee this? Maybe for the ones of you who do not know about hallucinations, also a simple example here. For what did Albert Einstein win the Nobel Prize? And the answer might be here. Albert Einstein won the Nobel Prize in physics in 1921 for his theory of relativity, and so on and so forth. And if you ask a person on the street, maybe, he or she might say, from a first glance, yeah, looks okay, why not? I take it. If you are more familiar with Albert Einstein, then you might know, well, he won the Nobel Prize, but unfortunately not for the theory of relativity, but some completely other aspect. He won it also in 1921, so that's correct. But you can also see there's a slight inconsistency. This is not what I really asked for, but okay. Okay, so how can we address this hallucination problem? And researchers, of course, have also thought about this. And one of the main or the key concepts they came up with is called retrieval augmented generation, RAG in short. This is about grounding now these outputs in verifiable facts. How does this work? Again, the example of question answering. How does CRISPR differ from traditional gene editing techniques? And the idea is now that instead of only asking our large language model with our internal knowledge, the idea is here, well, why not going to this external knowledge? We have knowledge graphs, databases, documents out there. We have, for example, all these millions of publications. So, and we really know if it's stated in this document, we can cite it. So why not using this information? In this case, for example, we have a publication which directly talks about here CRISPR. And you can see here it's talking about modern gene editing technology. So basically, the answer is in there. And you can use your large language model now to find, first of all, this publication and then reduce it to the answer which you want to have here. So CRISPR is faster, cheaper, and more precise than other techniques and so on, and with some details. So the output here is grounding in a scientific paper. You know it's coming from this publication. So you could just use it and you are done, you could say. And this is actually something which we have also developed in a more sophisticated setting in the scientific field, a demonstration system which is available online. And this is a scientific questioning system with a multi-agent RAG system. What do I mean by this? Well, it's very similar. We start with a question. So, for example, the user could ask, what is CRISPR-Cas9 and who invented it? And now we have different steps. We start, first of all, with a decomposing step, because as I told you in science, researchers could ask quite complex questions, maybe also combined, like here. So the first step would be to identify and say, what is CRISPR-Cas9? Who invented CRISPR-Cas9? And then for each of these sub-questions, we want to address them and provide the answer, basically. Second point is then the so-called hybrid retrieval, so the actual retrieval step. We then go into these millions of publications, find relevant documents, and then in another step, we have a generation step. So here, this item, by the way, highlights this agent. So this is basically a large language model, and assigning now the different answers to the different questions. So then we have question answering source pairs or tuplets. Because you might have different answers, and therefore we have another step, which is called a filtering or scoring step. The point is here that in science, you might have information which is maybe overlapping, outdated. So it's really not easy to, maybe you don't want to provide all this information to the user, and therefore you filter out some unrelevant content here. And finally, you have an answer generation step. So you want to provide the answer to the user in a very intuitive and nice way, as you can see here. This maybe sounds trivial to you, but on the other hand, you also need to make sure that this in-text citations work, that these references are formatted correctly, and you might have also data quality criteria regarding this text. It's coherent, concise, simple terms, you can make it short, long, and convincing or not, and so on. Yeah, this is a system which is available under SCWICE AI. Here's a demo, so you can really type in your question now. In this case, again, what is CRISPR-Cas9 and who invented it? And then you get, first of all, a very quickly, basically, here the sub-questions identified. Then it retrieves. In this case, we used the whole archive, which is about 2 million publications. And we basically make then each paragraph is then processed separately. And then you can see you can get here directly the answer. And with some here inline citations. Here are the references. And you can, of course, click on the publications, get more information there. And also quite interesting, maybe that you have directly here the context where this claim is stated, so that you can really have a trustworthy system and very quickly see, does this match? Is this what I want to see, what I want to have? OK, so feel free to try this out. This is a demo system, which I will also present in 1 month at the CIKM conference. Good. Again, the question. So this is apparently what I have created so far. What is left? What do I need to do? And I want to show this again by this same example. What is missing basically so far? Why are we not done? Why do I need to still continue here? Let's start with who invented CRISPR-Cas9 as an example. This sounded actually quite trivial question we have seen from our publication. In the sense of this CRISPR-Cas9 goes back to a publication from Chinnick and others. The main authors were here apparently Charpentier and Doudna, and they published a paper in 2012 in the Science journal. OK, so far so good. And you might maybe have heard of CRISPR so far because they won this Nobel Prize in Chemistry 2020. Now it gets a bit more complicated, actually. Well, there was unfortunately another paper, Gas and others, who also published 2012, basically the same technique. This was led by some author called Sixness, and they also published in a journal called PNAS or PNAS. So apparently publishing in Science is better than in PNAS, by the way. And yeah, we are still not done. On the other hand, CRISPR goes back, so the name was coined by Ruud Janssen in 2002. And to make it even more complicated, we had here papers from 2013 from Zhong and here from Mali and others, quite independently also, where they applied this technique to human cells. And they also published in Science, so apparently this is also not the key for a Nobel Prize. But then you have here the Chang lab and the Church lab, so who contribute to these papers. And these were led by George Church and Feng Chang. And this Feng Chan, for example, he is affiliated to the Broad Institute. Unfortunately, this Jennifer Doudna is affiliated with this University of Berkeley. And now the Broad Institute says, oh, Feng Chan was the first one. So there's still a patent dispute actually going on by Reuters. You can still see this online. And they say, maybe we can't win the Nobel Prize anymore, but we still want to have this patent, and we were really the first ones. OK. So this shows that basically still this relatively simple example, who invented CRISPR-Cas9, is not so easy to answer. And this cannot be, at least with a standard drug system, cannot really or can only be very hardly be addressed with a standard drug system, as you might have seen with maybe just operating on documents. So we need structured, curated knowledge to ground now these LLMs reliable. And this brings me to this concept of neurosymbolic AI. The idea is now to combine these two worlds. We have knowledge graphs on the one hand, where we structure and connect information or knowledge, as you have seen now. On the other hand, large language models also have an advantage. So they are good in extracting, in reasoning, and in generating information. So why not bring it together? The key question is how, of course. But overall, they're good in reasoning, understanding, and connecting, in this case, scientific knowledge at scale. Well, how to do this now? I have here one example brought with me again. This is based on a paper I have published and presented in August this year at the KDD conference. This is again from the biomedical domain. In biomedicine, and maybe in also many other disciplines, it's very important to identify causal relationships. So we're talking about causal discovery. Does, for example, smoking cause lung cancer? Does aspirin cause insomnia? And so on. And here again, you could ask your large language model. We have seen they're not so trustworthy often. On the other hand, you could use knowledge graphs. Maybe they can help here. And this was basically the idea which we have published last year. This is the ISWC from last year. And the idea is here, we might have knowledge graphs out there which are also in this biomedical domain. Maybe they are not so much modeling this causal information, but other relevant information. In this case, for example, drugs, diseases, and so on. For example, here, pariethyl causes hypercalcemia. And then we have another relation, this dihydrotestosterol resembles this pariethyl. And then it's relatively likely that here this latter one has a causal relationship to this first one here. And this is basically the basis, how can we integrate this knowledge graph information now with our large language models. And this is what we did, basically. The idea is here, we start with our knowledge graph. We extract some relevant substructures. Here, for example, between some genes, diseases, and so on, as I've just shown you. And then, a bit more complicated, but the idea is here that basically we can provide some input of these knowledge graphs as a prompt, so basically as an input to our large language model. And then the key is here that we just there's something going on, but the key is here that we have then a likelihood, how likely it is that is a causal relationship, yes or no, basically. Okay, so far so good. If you look at this picture more carefully, you might wonder, okay, but it's a little bit unsolved here. Which knowledge graph structure do I use which path? Why? Because if you think of a knowledge graph of, for example, Wikipedia, Wikidata, and all these knowledge graphs, they are very large in size. We have millions, maybe even billions of these nodes and edges. And the point is here, technically speaking, we cannot just feed in the whole knowledge graph into this large language model. This does not work. So we need a more sophisticated technique. And this is now this KDD paper idea. We have our knowledge graph. And then first we create here candidates of paths. How does A and B stand in relation to each other? For example, between lung cancer and smoking, for example, there's this path AEFB, ACDB, and so on and so forth. And then a first step would be here this subgraph relevancy estimation. The idea is here we ask a large language model, but giving this path here, giving this pair AB, for example, smoking lung cancer, how informative, how relevant is this with respect to the causal relationship? Give me a score. How relevant is it? How informative? And then we can basically create a very large data set based on this. So we have many, many of such pairs, paths, and scores. And then we can use this in a second step now for a subgraph ranking step. So here the second part is basically, this is not based on a large language model anymore, because this is not so good for ranking. But we can use, basically, we can train a dedicated so-called learning to rank based approach. And then we get the top K subgraphs, which you can use then for this causal discovery. So at the end, here, this top K subgraphs, here an example. So at the end, we get several of such graphs, which are apparently relevant, in this case, between some gene FGF6 and prostate cancer. And then we verbalize this, basically, as you can see here. And then we feed this in together with our variable pair, in this case between FGF6 and prostate cancer, maybe additional information, and then we can, our language model knows or can give us a likelihood how likely it is that there's a causal relationship between this variable pair. How good does this work? Well, in this case, here maybe some numbers jumping directly to the evaluation results. And first of all, here the blue ones are the approaches which we developed. Here are different data sets. So some are in this biomedical domain, some are more in the general domain. We also develop different large or use different language models. And one of the main points was, of course, to show, does it make sense to use a large language model in combination with a knowledge graph, or should I just use a large language model? And this is what I have highlighted here. No graph, basically, 33 F1 score, and here the best one is around 77 F1 score. So apparently it really makes a huge difference to combine knowledge graph information with the large language model and not just to use our large language model. So the point is here, we have the knowledge in our knowledge graph available, and the point is here just how to find this informative knowledge in our knowledge graph for our task at hand. So this was an example of the so-called neurosymbolic AI, where we combine knowledge graphs with large language models. Coming back to this initial motivation now, I started with this motivation of we have this scholarly information overload. We need to think about how to mitigate this. How can we help researchers out there? How can we still make sure that we have advancements in science? And therefore, my vision would be here need to work on trustworthy, personalized AI systems for scientists. So apparently, it's not enough to read papers. We need to think about more recommending methods. I'm not aware so far. Maybe I'm aware, or they were just recently published. The same with the data sets. I might have collaborators I might not know, I might not be aware so far if I'm new in the field, or maybe I have changed, or I have just published. And also research directions in general. And there might be more and more points out of this. Well, technically speaking, how does this work now? So here, again, this neurosymbolic AI approach could help. We start with all the scientific publications, and then we can create our biomedical, or in this case, just an academic knowledge graph overall. Then we have our knowledge-based knowledge graph and recommender system or search system. And then we have our user who can ask a question, for example, or give a research problem description. For example, I'm working on gene editing. What do you recommend to me? And then he or she might get the recommendation in CRISPR-Cas9 as an example. And then we might also have explanations and citations, as I have just shown you already. So from an end user perspective, we have our user here. He or she might provide, for example, a research problem description or a question, might get recommendations, and then maybe might also ask, why do you recommend this to me? And then the point is here, this AI system is able to provide an answer based on our knowledge graph where we have structured information available. And then we can verbalize it, as you can see here, in this case, because it's programmable DNA, and so on. Good. To summarize my presentation, I talked today a lot about this scholarly information overload. We are thrown in papers no one can keep up with, at least in fields like mine. This leads actually to a bigger question, the big question about how much research should AI take over. Then I talked more from a technical perspective that using knowledge graphs and large language models could be helpful. Knowledge graphs because they're good in structuring, connecting knowledge. Large language models because they're good in reasoning and generating text. And together, they can be very important for scientific discovery in the future to develop more trustworthy and transparent recommender systems and search systems. So my vision at the end would be to have this personalized, reliable AI in science. And what we have seen so far, this is still guided by humans. Well, on the other hand, if you go back to this initial question now, will AI replace scientists? Then the answer so far would be no, we don't need to care. On the other hand, I would say this is still controversially discussed. So, will not AI take over? And my point would be here that we see science which we need to take actually very seriously. So I can't stop here, but I want to show you two examples of this here, where life could change of researchers. And one is the AI scientist. Maybe you have heard of it. This is a paper published last year, and the whole idea is to kind of abolish this researcher. Let's do AI everything. How does this work? We have some idea generation. Normally, as a PhD student, we quite need some time to develop ideas. Even as quite established researchers, we have our difficulties. So the idea would be, why can't LLMs help here? We can basically get to the web, retrieve information, find gaps, can score ideas, and then we are done here. Then it goes into experiment iteration. In this case, it was done in the field of computer science. Quite convenient. In computer science, you can use LLMs to program. So you can create your programs automatically. You can also nowadays probably use or run these experiments on HPC actually quite a lot. And then the final step is here, this paper writing. Apparently, paper writing is still the key, at least in this vision paper here. And yeah, they let the LLM write the paper based on this data, based on this idea. And yeah, why not directly reviewing it right away, based on the same large language model or maybe another one. Yeah, and you might laugh, but yeah, when they even say, yeah, you can actually have a paper with $15 just running this script here, basically. They had actually some examples in there, so it works to some degree. And they actually have, so this is this AI scientist, as I said. Based on this AI scientist, a new paper came out, which is called the AI Scientist version 2. And they claim here they were the first one in creating this first peer-reviewed scientific publication. So basically, you can see there is something going on here. And interestingly, this is not the only one. I myself, I have attended the ACL conference this year, a conference, really one of the premium conferences, you can say, in the NLP field. 4,000 people, a lot is going on. And at least there was a workshop here where people have submitted a paper which was created based on AI. This was, here. We need to say in this case, a few things were done manually, but to a very large degree, this was done automatically. They have informed, by the way, this workshop organizers, so all is more or less fine. But is it really? I'm not sure. So to conclude, I would say AI is quite good in writing papers nowadays. But the point I wanted to make is, if you think of this AI scientist, for example, this was an end-to-end system. You could not know if you have the paper there, where was the error? Was it during the paper generation? Was it in the experiments? And so on. So my point would be here that the credibility still needs to rest on human validation and oversight. Humans still need to know what's basically going on. And in this regard, we still need our scientists. Yeah, I hope this was inspiring enough for you to get now your own opinion, build up your own opinion about will AI replace scientists in this way. Thank you very much for your attention.
So this is working. Good. What I've taken from this lecture is that we find ourselves amid a veritable tsunami of scientific publications, an abundance of scholarly knowledge increasing at a breakneck pace. And you, Michael, you showed us a way how to, well, navigate this vast expanding universe of scientific information by integrating reason and structure against the backdrop of philosophical and ethical clarity, as well as logical rigor and technical feasibility. So let's take this spirit of adventure into those topics into the Q&A session. As Lydia Lorenz, I am KIDS coordinator, and I am delighted to open the stage to dialogue, inspired by Michael's work and the lecture today. And I kindly ask you to contribute with your perspectives and your questions, no matter how seemingly trivial or profound, because you all are a part of enriching and furthering our shared understanding. And Michael has informed me that he even takes some questions in German, should the need arise. So, please engage. We have a first question over here. No, the one behind. Thank you.
Okay. Yes, it's on. Thanks a lot. You started your talk with a tsunami of publications, which is indicating a quantitative growth of knowledge. Can you, with the help of your methods, give us information if this coincides with qualitative growth? Do the number of ideas increase, or do we just see variations of the same ideas again and again?
First of all, yeah, a valid point. And this is actually a really interesting aspect which I want to address also in the future, which I have not mentioned here so far. In short, it's difficult to measure this, what I would call scientific advancements and so on, because you can't do it based on the citation count, not based on the publications. Maybe you can filter it basically what was published at top conference versus maybe only workshops and so on. So in short, it's hard. We need to really work on this, which, yeah, for example, has something also to do with developing AI or large language models, which are maybe also more capable with, for example, creativity and these other aspects, combining really information and not just repeating it and so on. But I'm personally actually quite pessimistic, yes, nowadays, that because if you think of these top conferences in the AI field, I talked about this ACL conference nowadays, 4,000 people. I have now submitted papers to conferences, 30,000 submissions. A few years ago, it was maybe below 1,000. This is something which we really also need to address. And therefore, in short, yes, I can work on recommending it, but on the other hand, yeah, we still have
my idea would be to specify what an idea is, somehow quantify.
Exactly, yeah.
The second question was over here. Paula? There, to you.
Yeah, thank you very much for this super interesting talk. As a former scientist myself, and now the transition to more data science, I have a technical question. I actually have a lot of questions. I would like to limit it to two that are related. First one is a more technical question. So especially when you use retrieval augmented generation and you use multiple sources, how does the retrieval deal with different terminologies that is behind the knowledge graphs or the ontologies behind the knowledge graphs? And what is related to that is, even if it were the same terminologies, like you could say, for example, in German, you could say Autor und Verfasser right? And how could AI or a large language model, well, probably the AI behind it, distinguish between well-respected journals and the so-called predatory journals, which goes in a similar direction like what we just have? Like, how can the quality be estimated?
So regarding the first aspect, which was more this technical about these RAG systems with the different sources. So first of all, it's if you use these LLMs, it's not just kind of keyword matching. It's more about that you have so-called vector databases, so you store these text documents often as vectors and so on. So even if you have some mismatch between words, your large language model is quite good in identifying this is almost the same and so on, I would say. Your point about the different sources is still an issue, I would say, is the standard RAG systems don't really address this so far. You always need to think, that's why, for example, we have also developed this own sophisticated RAG approach. So there you basically need to, at least nowadays it's still in research, you still need to think about, for example, these different sources, are they on the same level? Do you want to wait one more? And are they based on, for example, the same scientific discipline? You might want to have different large language models for this and so on. So this is something you might want to address. That's correct, yes. Maybe very shortly regarding the second one, it goes in this direction, if I understood your correction correctly, again about this, what makes good scientific research, how can you identify this? And I would say you can do it to some degree, but to some degree it's really difficult. So if you think of, for example, what could help is, again, structure, I would say. If you know, okay, this comes from this journal and you have metadata about it or connections about in the past, these and these authors, maybe these and these authors who have published in similar venues but not in top ones, then you can basically predict somehow that this journal might not be so good or so. This would be my answer.
We have a third question over there.
Okay, thank you. So I don't have the IT or AI background, so maybe it doesn't make so much sense. But I was wondering, when you were talking about the neurosymbolic AI, you said it uses the graphs, and then the large language model kind of makes a ranking. And as far as I understand large language models, they are based on recognition of patterns and stuff. So I'm wondering how biases play an important role in actually making the ranking. Like, what are they trained on? What kind of data and information do they use in order to make their ranking? And can we really get the bias out there, or is it still an issue? Because it's definitely still an issue in large language models.
Yeah, in short, bias is always an issue, I would say, or at least which you need to think of or be aware of. Yes, so as one example, in this case, I use these large language models mainly for this dataset creation. Large language models are actually not so good in ranking. They are good in next token prediction, so they are good in generating text, but not to decide this one is better than the other one, and so on. This would be my answer, yes. And then the question is how to feed this in. And this is a difficult task. The point is here that maybe this is a bit visible here, in the sense of that on the one hand you have this knowledge graph structure. On the other hand, you just have text input output, so you have this sequence, and this is not compatible. And the question is, yes, how can you bring this together? And you're right. So in this case, you often try to select the subsets and then you sequentialize it basically, and then you feed it in to make it into some text which the language model can understand. That's the most common way, I would say. I hope I addressed your question correctly. If not, then please rephrase. I forgot maybe some part. Okay.
You can take this over snacks and drinks later on if you want to go into that further. We have a question over here and then in the middle over there. And then.
Yeah, thanks for this wonderful talk. So this is a question that comes from philosophy of science. And in philosophy of science, one major take-home lesson is when we look at science is that there is never a one-size-fits-all solution or description of what happens in science. So I'm wondering here what various functions AI can play in science and whether it might be more or less conducive to some rather than others. So, for example, thinking of the many aspects of the research cycle, coming up with ideas, designing experiments, performing experiments, deciding about grants, money being allocated. Where do you see the most potential in the short run and near future for the AI scientist?
Mm-hmm. Good point. Let's maybe go back to this AI scientist. So, first of all, it depends heavily on the domain, I would say. In computer science, it's quite good because you can generate code based on LLMs. Of course, it's still not perfect, and this only works for some relatively toy examples or at least small cases, but still it works to some degree. So first of all, yeah, it depends on the domain. If you are in, let's call it hard science, like physics and so on, they need to make experiments. It's not so hard, but maybe you can at least get recommendations which experiment setting you want to try out and so on. If you go through this, here regarding this idea generation and scoring I see some potential and I see some papers already coming up. So here, people already thought about it. And yeah, I like this. This is again about creativity and so on. On the other hand, it's again about this definition what makes good science. So this is, I would say, rather a recombination. But if you think of really a fundamental paper, you want to publish now a new theory of relativity, let's say, then probably this is still hard to get there. And then, yeah, so here, second point, experimentation really depends, I would say, next 1-2 years, we don't need to worry too much. Then AI is quite good in, of course, text generation and so on. So if you have all this information there, in just making a draft and so on might be quite doable and so on. The reviewing is something which I'm more skeptical, I would say. So in short, where are they quite good in? Of course, they're good in text generation and in combining information, summarizing it, and so on. So if you have all the information out there and just about presenting it nicely, their AI is good. And hope this answered your questions.
After you pose your question, if you could further put it down, Professor Staudinger is next after you.
Ralf Müller-Pfefferkorn. I believe science can be both a scientific discovery, a structured approach using all the knowledge we have, but on the other side, some accidental idea abstracting from one concept to another one. Currently, we are fighting hallucinations in LLMs as a bad thing by using your knowledge graphs or recs. Do you think that we could also use some kind of hallucination for scientific discovery in such AI systems?
In short, yes, and I've also already submitted a paper in this regard, which is directly about using hallucinations, in this case, for drug discovery. Main author is sitting here, by the way.
Okay.
You might want to talk to this. This is currently under review, and this is really about, in short, this is about drug discovery. For example, if you have molecules and you want to identify is this toxic or not, and then you can just feed in this molecule sequence in this MIA structure directly into your LLM, or you can generate text. And this additional description might have hallucinations, but interestingly, doesn't matter so much. It really depends on the model, but sometimes you really have this effect that you can get better results. And this shows that apparently these hallucinations have something to do with this recombination of ideas, as you also pointed out. So I think, yeah, there is a point of potential in the future on that.
Yeah, if you could send the microphone on its way to Professor Staudinger, I'd be very glad. Thank you.
Thanks also from my side for this interesting talk. I want to come back actually to your combination between knowledge graphs and language models, and trying to really find out where the validation merit of knowledge graphs lies. Because the way I understand you using them is as a kind of grounding and disciplining language models. And from my very naive and amateur understanding, one of the basic mechanisms of language models is probability driven. And so my very naive assumption then is that knowledge graphs are not probability driven, but are maybe using matching algorithms or something like that. Mm-hmm. That for me would be a first question. Mm-hmm. And my second point is we are currently at a state, not so much when we go to the level of research papers, but when we look at the abundance of raw data that is created in various fields of research, that we see at the forefront of epistemic insight. It is the combination of large language models with actually theoretically and mathematically informed constraints that are imposed on the language models. And if you would now compare that type of algorithm-driven, theory-driven, mathematics-driven constraint with a knowledge graph constraint, have you ever thought about that? Or is it a completely off thought? I mean, admittedly, I'm an amateur, so I'm just listening and...
Totally valid questions, yes. So the first one about this neurosymbolic AI and this combination, yes. Well, with knowledge graphs, in short, so first of all, it's about this grounding, but then it's also about making these systems trustworthy and especially explainable afterwards. So that you can really say this information, maybe let's have this other example. If you have the output that you can really go back to your knowledge graph and you can say this comes from, for example, this node and it's connected to this paper. And so basically it's also about citing in information and so on.
Yeah, but I mean, at the base, I mean, still the knowledge graphs organize existing knowledge, right? Mm-hmm. So my question is, they are basically about looking, matching, and then counting, whereas the language models are doing sort of like a probability-driven, Bayesian-driven algorithm to organize knowledge. So I really like to understand where the validation power comes from, except for that I know the paper that it comes from. But, you know, honestly, I mean, if the knowledge graph is based on 1,000 papers, I can still not look it up.
Yes,
maybe I misunderstand what knowledge graphs do.
Okay. Yeah, the power about this reasoning and explainability, this is mainly in the language models, yes. It's just in the background, there is this knowledge graph to have just a structure of how this information is connected, yes, yes. And
how is that structure established?
Yeah, this is about, the question is how to create knowledge graphs, which I have. Yes, which I have not addressed here. I'm sorry. This is.
Yeah, but that's my key question in order to understand whether they have a validation power or not in my head.
I see. Yes, yes. There are different techniques. You can do it automatically. In theory, you can do it manually. If you do it automatically, state-of-the-art approaches also use LLMs, actually. Then it's quite interesting because you have a turnaround. And you. Yes, exactly. And then the question is how to remove hallucinations there. But yeah, this would be too much for my talk today. That's why I have addressed this in my inauguration lecture last year. Yeah, so I have also worked on information extraction, by the way, and it's not so difficult to, it's good in extracting these concepts. These relations are already quite complex in short, yes, yes, exactly. And especially in these very specific fields in science, if you think of very complex terms. And you're totally right, if you think of scientific knowledge, you have, for example, conditions or other. So it's not just that you say this is the case, but you often have this prepositions, values, which is just associated. You cannot just say this is correct, but often it's correct in this context and so on, yes. And there also LLMs can help, yes, yes. So in the future, we need to think some knowledge might be in knowledge graphs, some might be more in our large language model, and we need to combine this somehow, yes.
And my second question, have you ever thought about using theoretically based constraints?
There are a few ideas out there, yes. So far, I've mainly focused on the main task about how to create knowledge graphs, how to combine it with large language models. In short, there are a few words, but again, the question is how to operationalize.
We do have a next question over here. No, one more down. He was further. He was just first, and then we have another one over there, and then it's your turn.
Hello, thank you very much for your very informative lecture today. I learned something. My name is Ivan Godimenko, and I am the adjunct professor at the Faculty of Computer Science. Now, today I had a wonderful students in my lecture, and I keep asking myself, what would you recommend for these wonderful young students who are eager to learn something in the current world of papers? I presume, as I did in my PhD, I could brute force the papers which were relevant. In my opinion, now it's not possible anymore. What would you recommend these students, and which impact does it have to the learning process as such? Thank you.
I would say it didn't change so much. I would still say first, I don't know the exact setting, but I would recommend still you should be driven by curiosity and the topics you like and so on, I would say. And then it's about, if you ask more about which papers to select nowadays, as it gets more difficult. It's basically what you also recommend students basically nowadays, that you give indications about was it peer-reviewed, was it published at good conferences, for example, and then the other point would be more about topics. All such topics you can address this easily, yeah.
Any good tools for that?
Any?
Any good tools for that?
Any good tools? use my question answering system, Squai. Where you can just answer questions, you get directly references. This could be a good start, I would say. Yes. Good.
Thank you. Your turn now.
Okay, so thank you very much for the nice talk. My name is Anita Behm. I'm from the Faculty of Mathematics. And I tried out your Squai during the talk and asked about my topic of PhD thesis. So actually it worked quite well. So he gives me a nice overview of the type of processes I work on. And then there are the 5 references, some papers proposed, which were, from my point of view, rather randomly chosen. Okay, I mean, I'm a probabilist, so that's okay, but you said you have some filter in there, right? So you choose some sort of which publications are important now. So the 5 I've seen in this example, I mean, it's just one example, were not really the ones I would have expected, so to say. Mm-hmm. But in various points of your talk, you also had this like, okay, so the science paper is maybe better than PNAS and so on. So will we just now order papers by, which journal they are in, or are the authors more important? And is this then a reinforcing loop that at the end only science papers are important and everything else is not seen because the system that we use to find information orders by some, by age index and so on, and it will be
right.
Yeah, so that's, I guess you got the point.
Mm-hmm. Yes. In short, this is more or less also in this direction of this bias aspect, which we had beforehand. I totally agree. I've also published a survey some years ago about bias in scholarly recommender systems. And indeed, yes, you can have different biases which you need to be aware of, and especially in such settings, they can really reinforce the effects. You have this, everyone knows the Mathias effect, but you also have visibility bias, or the top first ranked ones are just the most clicked ones. I personally still want to do it more this what we call content-based recommendations, so not looking at authors and age index and so on, but more going via the content. But then still your question is, of course, what are these, for example, recommender systems built on? In my example, I had all archive papers until I think end of 2024, which was just some decision because it was freely available, simply said. But you can directly get a bias in there already and so on, yes. So I see the point, yes, and you need to be aware of it, yes, and showing that, maybe we can discuss it later if the other ones were not. I mean, this was still a relatively standard drug system, I agree, if you're more interested in other, conflicting ideas, then you might, as I said, then we need to think more about further approaches in the future, yes.
I am sorry, I have 2 more questions in queue, and you can take it into the reception. The question before last, and then we have one up, and then we'll wrap up.
Okay, thank you very much. I'm Till. Hi, I'm from the Helmholtz AI team at HZDR. And I would like to know, so in your daily life as a scientist, what are the 2 use cases where large language models make your life easier? So what are the 2 most prominent use cases, and maybe also 2 use cases where you think, well, they're not really helpful and maybe also will not be in the foreseeable future?
They're very good in, as I mentioned, in summarizing text and so on, and more in these question answering settings. You have one, for example, one paper, and you directly want to ask something about it also, I would say. They're also very good in if just writing, for example, text or any kind of structured text in a nice way. If you have, for example, notes and you just want to have it written very well, I would say. Where it's not so good, we also talked a little bit about this one is, I mean, obviously I tried it out for many aspects, and also I use it, of course, a lot. But the point is that, if it gets more, for example, regarding this idea generation, more about this creativity aspects and so on, this would be one point which comes to my mind where these large language models, still have some deficits and so on. And yes, and then it's more about, connecting knowledge and what I want to address here in the future more about this, if you have conflicting information, partially overlapping information, such aspects basically, that when you just not have here the answer 42, but you have where it's more complicated. Yes.
Thank you.
Last question up in the back row before we wrap up. Thank you.
Thank you for the nice talk. So my question is regarding the AI scientists. I understood most of the steps. The only thing I was kind of at a loss about was the final step. You seem to be yourself a bit skeptical of having the LLMs review the paper, right? So my question is kind of, wouldn't reviewing a paper require the same kinds of informations, the same kind of, knowledge trees, and thereby kind of, you can't really validate if you just run everything against the same data you use to generate your paper. So I'd imagine, how does having a LLM review a paper even make much sense if that paper is generated by an LLM in the first place?
Yeah, that's correct. So I was just skeptical in the sense of that you maybe should use another large language model for this when you want to review it, because otherwise it has the same opinion or so. So nowadays, of course, there are also this, you can fine-tune it or adapt it more to specific settings. You can, nowadays there's also this direction of that you have LLMs as an expert, LLMs as a judge, and so on. So you can also ask different large language models and get an agreement, basically, and so on. So I would say, yeah, of course, it makes sense to get some review. My point was also rather from a scientific community perspective, we need to think about if this peer reviewing, is still what we want to do. Can be done by LLMs, because it might be still something where LLMs don't know and so on. But you trust this. Then this paper is published forever, basically, and then further researchers just rely that it has a good quality. This was my main point.
Right, so this exaggerates the problem essentially, because now AI agreed on papers and now AI agrees on AI agreed on papers, right?
Exactly, yeah.
All right, I got you.
Thank you for your contributions, and while proving quite empirically that the quest for synthesis is not only about computation but conversation. And these are for you as a token of our gratitude for your work and appreciation of your work and future endeavors as Kids and Scuds AI. Before I let you out to have a few snacks and drinks, we will be taking a picture with Professor Staudinger, Professor Nagel, and Professor Bayer just in front of this beautiful kids roll-up. And any further questions will be asked outside. And before I let you out, I have been asked, please sign, when you go out, please sign one of those two papers, depending on whether you're external or an internal, either a member or not a member of TU Dresden. Thank you so much.
Thank you for coming.
Wir machen das da vorne.
Ja.